This is Learning Assessment Problem 7.6. In this problem we have a circuit with an energy storage element, which is an inductor, and a switch which operates at time 0, and we're asked to determine the expression for the voltage V sub O as a function of time for time greater than 0. We'll be applying the step-by-step approach to solving this first-order circuit problem. Step 1 in that approach is to assume the variable of interest, which is the VO of t for us, is equal to a K1 coefficient plus K2 e to the minus t divided by tau, where tau is a time constant appropriate for this circuit. The second step is to consider the time t less than 0. We'll choose t equals 0 minus. The switch is still closed at this instant, and we are in the steady state condition. And what we want to find is our energy storage element property. What we want to determine is the current in the inductor at this time, IL at 0 minus. For the conditions indicated, the inductor looks like a short circuit, and we'll proceed to determine that IL is 0 minus. Perhaps the indirect way to solve for this would be to do a nodal analysis. And consider the node voltage VO at 0 minus appearing at the top of the circuit. That happens to be the same as the desired voltage that we're looking for at this instant. So we have one node voltage, two voltage sources, and we'll choose the bottom of the circuit as our reference node. So if we do the nodal analysis, we'll have VO divided by 2 ohms. If we do this nodal analysis, we'll have summing currents at that top VO node. We'll have VO divided by 2 ohms for the current flowing downward through the right-hand 2 ohm resistor, plus VO minus 12 volts divided by 2 ohms, the current flowing into the 12 volt source, and then plus VO plus 4 volts for the current flowing into the negative 4 volt source divided by 2 ohms, and this is equal to 0. Rearranging terms, we have VO times 1 over 2 ohms plus 1 over 2 ohms plus 1 over 2 ohms is equal to 12 over 2 minus 4 over 2 is equal to 4 amps. So we have 3/2 VO, that's 3 over 2 ohms, so we have 3 over 2 ohms times VO at 0 minus is equal to 4 amperes, and this gives us that VO at 0 minus is equal to 8/3 volt. What we're really seeking here is the IL at 0 minus, which will be this VO at 0 minus divided by the 2 ohms. Recall that the inductor looks like a short circuit at this instant. This will be 8/3 volt divided by 2 ohms, and this current will be then 4/3 amp. So that's step 2 in the procedure. Step 3, we'll consider the time t equals 0 plus. So at t equals 0 plus, we have this equivalent circuit where we've replaced the inductor by its equivalent current at t equals 0 minus. We placed a current source there. This property inductor is that the current is continuous, so we have IL at 0 minus is equal to IL at 0 plus. And this will enable us to calculate the VO at 0 plus is equal to IL 0 plus we can calculate the VO at 0 plus is equal to 2 ohms times IL at 0 plus, or VO at 0 plus is equal to 2 times 4/3 amp, or VO at 0 plus is equal to 8/3 volt, probably a quantity which we've seen already. Now, step 4 in the step-by-step procedure will be to consider the circuit behavior as t goes to infinity. This will be a steady state situation again, and the equivalent circuit for that time will be the inductor again behaving as a short circuit, and call it that switch is open, so we do not have the central branch involved in this time period. So we now want to determine this VO at infinity. This will be 12 volt source times 2 ohms divided by 2 ohms plus 2 ohms, voltage divider relationship, or VO at infinity is equal to 6 volts. Now we can go to the 5th step in the step-by-step approach, and that is to calculate the time constant. So our equivalent circuit to determine the Thevenin resistance appears by removing the inductor from the circuit and drawing the remainder of the circuit. So we have 2 ohms, 2 ohms, 12 volts, and this will be the Thevenin resistance seen by the inductor. Remember that we set the 12 volts source to 0, and then we look at the passive resistance in the circuit. R Thevenin will be 2 ohms plus 2 ohms, or R Thevenin is equal to 4 ohms. Then the time constant will be L divided by R Thevenin, which is equal to 2 henries for the inductor divided by 4 ohms. This is 1/2 second. The units of the time constant are time. And then the final step in the step-by-step approach is to evaluate those coefficients which we had in our original equation. That is, VO at 0 plus will be K1 plus K2, since the time constant at t equals 0, that exponential term has a value of unity. And from our previous work, this is equal to 8/3 volt. And then V0 at infinity will equal just the coefficient K1, and that is equal to 6 volts. Result of this is that we can solve for K2 is equal to 8/3 volt minus 6 volts is equal to minus 10/3 volt for K2. K1 is 6 volts. So we can combine all of this into our assumed expression for the voltage behavior. This will equal K1 plus K2 e to the minus t over tau. This is equal to 6 volts minus 10/3 e to the minus t over 1/2 second volt, or VO of t is equal to 6 minus 10/3 e to the minus 2t volts.